All right, so I changed the title of my talk, actually. I'm going to, since Jorn Vanderbos and Jörg Schmalen will talk about some topology, I decided to just talk about correlated phenomena. In the spirit of discussions, I just want to tell you the latest thing we've been doing. So, yeah, so I'm going to talk about these two works. One is with Yiming Wu, who is a postdoc in Stanford, and Yushu Wang from Florida. Was just published in the best journal ever. And anyway, and the other one, which we just posted in archive with my student Anand Chakraborty and my collaborator Turan Birol and his student Fan Yang. All right, so I will talk about two separate topics. The first one is superconductivity, but I'm going to talk about how altermagnetic fluctuations can promote superconductivity. And then I'm going to talk a little bit about some recent work about how you can get altermagnetism on the Kagome lattice, collinear altermagnetism. Okay, so let's start. This is the work I mentioned to you. Since we heard beautiful introductions from Libor and from Tomasz yesterday, I'm going to go right to the chase without any mercy. So this is a common theme if you do correlated systems. You like to see a magnetic phase that undergoes a transition at a finite temperature, and then you apply some non-thermal parameter, density, pressure, strain, or whatever you want, suppress this to zero, and then near a putative quantum critical point to get superconductivity, right? So we all love this. This has been seen in many materials. I was going to put a cuprate here, but that would make me lose 15 minutes of my talk. So I'm just going to show two different ones. One,
a real example.
Yeah, see? Iron-based, see what happens? Iron-based superconductors. This is an antiferromagnetic phase. This is a very widely studied phase diagram. You suppress it with electron doping, and you see a superconducting phase that we believe, or there's very strong evidence, it is. S plus minus is an unconventional superconducting state. This here is an example of a ferromagnetism, or at least that's what a lot of people nowadays consider the case. This axis is not continuous, but you have these uranium-based systems. You start with uranium germanium-2, which is a ferromagnet. You go here to uranium tellurium-2, which is not a ferromagnet, but is a superconductor. And this is the best candidate, I believe, that we have for a triplet superconductor. Okay? Until 20 years from now, someone says it's singlet. But anyway, this topic has been studied.
How about UPT3? UPT3.
That's also great.
No comments without the microphone.
Thank you. So this has been studied a lot, this problem. How can magnetic fluctuations promote conventional superconductivity? I put some names here, and if your name is not here, don't be mad. There's not enough space to put everyone that has worked. It's a very rich problem. There are lots of different methods, lots of different approaches. But what we know for sure is that generically, if you have antiferromagnetic fluctuations, we usually expect that we're going to get singlet pairing. Okay? Could be D wave, it could be extended S wave, it depends on the Fermi surface. Fermi surface actually affects what we have. And if we have ferromagnetic fluctuations, the pair interaction that it mediates usually is triplet. We classified some of these in this paper, but I think this is, again, very well established and understood, right? Then when you think about this and you go to altermagnets, you say, okay, altermagnets, they don't break translational symmetry like antiferromagnet. And they also, they break time reversal and rotational symmetry together, preserve translation. So if you just do a very straightforward analysis, you expect that you're going to get triplet pairing. Okay? And this is, again, because it breaks the same, because of the symmetries that it breaks. However, even very early on, Igor actually had this, it's not even a paper, it's just some notes that he posted on archive about superconductivity and altermagnetism. And he pointed out something that is actually very interesting. That's going to very much be the main point of my talk. Is that sure, in the long wave, that's not how he's saying, I'm going to paraphrase, but the point is that you have, as we saw yesterday, altermagnetism has a sublattice degrees of freedom. You need that sublattice to enforce the rotation between the rotation symmetry between the two sublattices. So you have an internal structure. And he says here, no, this internal structure could give rise to different pairing states. Sorry. And that's going to be the main point of my talk. I'm going to show you that when you include this internal structure, you do get things that you would not get if you just consider the long wavelength limit. Okay? that's the summary of what I'm going to say. For that, I need a model, okay? And I'm going to tell you about the Lib lattice model. I know that many of you have worked on this model, but I'm just going to tell you, construct step by step to motivate why this model we expect to get something other than triplet, okay? Again, let me just start and then I'll make some comments. So you can start with the usual antiferromagnet, okay? That's going to be important point. And then I'm going to declare that my new unit cell has 2 atoms. And I rotate by 45 degrees, so you don't need to be doing that the entire talk, okay? So you have 2 atoms per unit cell. Blue and red are spin up and spin down. This is the simplest, I think, altermagnetic phase that you can think of. And now we're going to do a toy model, low energy model. I was told not to say toy because people think we're joking, but anyway. We have nearest neighbor hopping, next nearest neighbor hopping. So I'm going to do something even simpler. I'm going to just declare that there is some degree of freedom, some interaction that gives altermagnet. I know Brian and Danny are going to talk more about this. But this is just that n is the staggered magnetization. I have 2 degrees of freedom. I have the sublattice, which I'm going to call tau. And I have the spin that I'm going to call sigma. You can write down the tight binding model, couple the electrons. And tau z tells me I have different signs on the different sublattices. And then when you plot the band structure, you expect 4 bands, and you see 2 spin degenerate bands. You don't see altermagnetism. And that's not surprising because I didn't do anything other than take an antiferromagnet and express in a different basis. Okay, so it's not surprising. What is missing here is the key point of altermagnets, which is that the lattice has to tell me that these 2 environments are not the same, but they are related by a rotational symmetry. And in this model, you can get this very easily, and that's now the Lib lattice. You just put some non-magnetic atoms here on the sides. I'm going to consider that the energy is so high that I can ignore them. And the effect of, let's say, integrating out this or considering perturbatively this atom is that now I have a different hopping between, next nearest neighbor hopping between x and y. And if I include these 2, it's nicer to define their difference, because that's what tells me that the lattice is a lattice. This Lib lattice and these 2 are related by rotational symmetry. And then you get nicely the altermagnetic splitting, okay? So this is a simple model, but it has all the ingredients that I need. It has sublattice degrees of freedom. And it tells me that without the lattice, this hopping anisotropy, it is just an antiferromagnet, okay? So this was this was done, this model here with Jorn Vanderbos, who is here, and Dani Antonenko. Asla Sudbo had a related model, though with some small difference, but similar model before. Now, before you say, like the referee of our paper said, Lib lattice is a thing that exists in the head of theorists. Yes, correct, but they also exist in nature. As Eduardo called me when I told him in his office, this is the anti-cuprate, which I like very much. I should say that this is the anti-cuprate model, because in these 2 materials, this is a Mott insulator. This is the lanthanum manganese. This is an oxidnictide. It was actually studied about 15 years ago in the context of iron-based superconductors, because the Mott insulator. And here you see that the manganese are on the sides, and the on the bonds, and the oxygen is on the sides. And the reported magnetic state is precisely an altermagnet. Okay? Now there's another one, which is also was mentioned, I believe, by Libor yesterday, which is this vanadium 2 selenium 2 oxygen with some alkaline earth, or potassium, or could be also rubidium. But same story, you have here vanadium up and down, oxygen on the side. So, and this one here, the vanadium selenium, there is a metal, so people have done ARPAs in these 2 papers, spin resolved ARPAs. And you see clearly the D-wave spin splitting. So yeah, it's a model, but it's not a bad model. Now you can ask me, is there any evidence for a superconductor that arises near an altermagnetic instability?
Rafael,
yes.
Is anyone doped?
Say it again?
Is anyone doped?
No, that's exactly what I was going to say. These are, what we are proposing is that maybe you can get to that phase diagram by doping this very much like you do in the cuprates. And this one is already a metal, so maybe you're applying pressure, okay? So we're waiting for that. Okay, so now Thomas yesterday talked about momentum-Yoke instabilities. And I want to point out now the difference. From a symmetry perspective, they're identical. There's no difference. Okay? But there is a matter of mechanism. Of course, in the long wavelength limit, I can sit here near the chemical potential here, and I can do an expansion. And you do see some similarity, but you also see one difference, right? So this is just the dispersion of a state that underwent a momentum-Yoke instability in the L equals 2 spin triplet channel. You see exactly the DOA form factor, and this is the momentum-Yoke order parameter. You see the same if you take the Hamiltonian I told you and expand near the gamma point, you sit here, but now you see a difference. You see two energy scales. You see J times N, this is just the magnetic energy scale, but you also see our beloved TD here, TD over T1. This tells me how much the lattice is contributing to that. And this is because I have these two energy scales that I have more options for pairing than if I had just this problem. Okay? All right, so that's exactly what I just said. And the idea is that if I'm an energy, if this TD over T1 is not large enough, or even it sets a scale, if I'm approaching a quantum critical point, or if I'm changing frequency or temperature, there is an energy scale where this interaction here should not be that important. And my system should look more like an antiferromagnet in practice for its fluctuation spectrum than an altermagnet. Therefore, I should be able to see some singlet. That was our intuition. Okay? And to some extent, that's what we found. Any questions before I dive in the math?
Can I have a question?
Yes, absolutely.
So you're saying that only in this model, because of the richer structure of the order parameter, I can have something beyond S wave?
No, this gives you triplet.
Sorry, beyond. No, you said ordinary
Ordinary ferromagnet.
ordinary antiferromagnet gives you singlet, right?
Right, but ordinary ferromagnets give you triplet.
Triplet. But here, even independent of the microscopic structure, if you see these Fermi surfaces, you immediately see that you can get both, right?
You were talking about what happens inside the antiferromagnetic, the altermagnetic phase. I'm not talking about that regime. I'm asking the regime where the altermagnetic fluctuations are providing me the pairing. So I'm in the disordered state. I'm approaching the ordered state. Okay. So what you're describing, absolutely, and that's, I think, Eduardo going to talk about it, right? But I'm talking about the altermagnetic fluctuations giving the pairing mechanism, the pairing glue. Okay, so that's the difference.
So it's the proximity.
Yeah, so just to make it clear, if I go back here to this phase diagram, I'm talking about what happens in this regime. What you're talking about is if I start here, and maybe there's some other pair interaction that is unrelated to altermagnetic fluctuations, could be just standard electron phonon or whatever, that's a different regime. Okay? All right. So now I'm going to go on to some of the details of what we did. I mean, that's what happens when you write two papers with two different people, right? They change the notation, and I forget to change. So anyway, it's a little bit different, but it's the same story. This is our Lib lattice. T is the nearest neighbor hopping now. T prime is the next nearest neighbor. And we do something that people in the correlated community have done for ages, right? So you say, look, I have my free electrons that live on this lattice. Then I have altermagnetic fluctuations, and here I'm just saying there's some interaction that gives rise to it, and again, there are models that give that. So for now, I'm just going to adjust the position of this quantum critical point by this parameter R. J is just an energy scale. This is the form of the susceptibility that you get by calculating the particle hole bubble, but it's just what appears from symmetry. Okay? So I'm going to control how close I am to this by changing R over J. So this is now the action or the properties of these altermagnetic fluctuations, and this is the coupling, Yukawa coupling between them. Okay. Now, obviously, this is if I know how to solve this problem here, I don't know. I was going to be rich, but probably I wouldn't. But anyway, what we're going to do is solve as we approach it, and then we use perturbation theory, knowing that close enough to the QCP, this breaks down. Okay. All right. So to give you an idea of where the new physics comes from, I'm going to go a little bit more technical here and tell you about my operator. So I have two sublattices, A and B, and two spins, right? So I have to form a pair out of this object that has four components. I can express these two components in terms of two Pauli matrices, spin and sublattice. Now the key point is that the sublattice is very special. If you take my Hamiltonian, the one that I wrote, okay, and you shift it by a primitive reciprocal lattice vector, meaning 2 pi, 0, 0, 2 pi, it's not periodic, but it has this unitary transformation based on tau 3. And that's just because I have these two sublattices, they are displaced by half of a lattice vector. It was pointed out in the paper by, where's Daniel? Oh, you're here. Daniel pointed out this, and let me just point out also that this general structure of this model does not work only for the Lib lattice, but is much more general. So there's a whole family of models. And what I'm saying, the conclusion should hold to some extent. Okay? Now, because of this property, now you can see something that is very interesting. I can form pairing between electrons from the same sublattice. That would be tau 0 or tau z. Okay? Or I can have pairing from electrons from two different sublattices, tau x and tau y. It turns out that because of this property, when I look at the gap function, it's even or odd under a shift by this reciprocal lattice vector. Okay? So this is a key point, and that's what's going to allow me to have singlet. And you see how the sublattice is going to strongly affect the property. So if it's odd on the sublattice, or sorry, if it's electrons from the different sublattices, we're going to call this intra-unit cell pairing. And the pairing function is going to get a minus sign when I go to the next Brillouin-Zahn. And that will imply that I'm going to have nodes on the Brillouin-Zahn boundary, okay? Which doesn't happen if I have the other kind of pairing. So we can now do standard trick, which is to write down general interaction, and then the interaction mediated by these altermagnetic order parameters. That is in here just the susceptibility, okay? And I'm not going to show you the details. Of course, I'm just saying that there's a standard procedure. You use something called Fier's identities, and you ask which pair interactions or which channels are attractive for that pairing, mediated by altermagnetic fluctuations. Okay? And you find four different states. So let me go over one by one. Okay? Any questions?
Is it like, oh, sorry.
This one?
Yeah, is this like an exact relation?
Yeah, it's exact, and it follows precisely because of there are many ways you can think of that. You can just think of this as like a J1 term, for example. That's
okay. But you wouldn't get this out of the dispersion relation of your...
Oh, you do, absolutely.
Oh, okay.
If you just take this dispersion, you calculate the polarization bubble, you get exactly that.
Okay, thank you.
Okay? All right. So the first state we get is what we would have expected from the beginning. Is a P wave, and that involves electrons from the same sublattice. Okay? So here's the forms if you don't believe me, but as I mentioned, right, you only have same sublattice pairing. There are four of them. You can interpret them as the spin 1 with SZ equals +1 and -1. You see, where is SZ equals 0? You see soon. But it's just a standard P wave form factor that you get. All right? So this is what you generally expect from a Pomerantziuk instability, if I had just told you that.
There's no spillover interaction.
No, there isn't. When I turn it on, nothing really changes except for the intra-unit cell pairing. Okay, so we include it later, but most of it will be irrelevant for what I'm saying. It's vibrating. I don't know if that means anything. Anyway, okay. Now we get the... It's half an hour. Don't steal my time.
It's not 20 plus 10. It's 30 minutes.
It's 45 minus 15. That's how it is. Eduardo, don't steal my time. The other thing that you get is this P prime wave, and we started at 9:05, so yeah, there's an additional 5 minutes. Now we get the first intra-unit cell pairing state. That involves electrons from different sublattices. And you can see here that these form factors, because of this over 2 that you get, it has this property that when I go to the next Brillouin-Zahn, I get a minus sign. So this is an intra-unit cell pairing, and it is the SZ equals 0 component from that triplet state. Okay? So you see that they already split in this level. When I said I don't have spin-orbit coupling, I was kind of lying to you, because I'm assuming the spins point out of the plane. So I don't have I don't have the spin-orbit coupling term in my Hamiltonian, but I'm assuming that it's selected up, okay? Just to clarify, that's why I split the SZ. Now we get the singlet states as well, okay? So these are singlet states that I get. The first one is a dxy wave, and it makes sense. If I had shown you antiferromagnetic fluctuations, you'd have guessed dx squared minus y squared. The reason why it's dxy is just because they're rotated by 45 degrees, right? And again, it has the sign change when I go to the next Brillouin zone. And because of this tau 1, whenever my Fermi surface has a pure sublattice state, it has to have a node. And you can prove that every time you go to the Brillouin zone boundary, that's what happens. So you get nodes on the Brillouin zone boundaries. Again, this could be accidental nodes, but I'm just going to mention that to you. Okay? And the last state is an extended S wave. Again, nothing very different than what you'd expect if you had antiferromagnetic fluctuations, but this is an intra-unit cell pairing, and that's why the altermagnetic part is important. Same story, singlet, S wave. Now I have actually linear nodes that can become quadratic when I add spin orbit coupling. Okay? Now, which of these states is realized? Now we have these 4 possibilities. We can simply compare their eigenvalues of the linearized gap equation. And as you know, this will depend on the Fermi surface, okay? So when you, this model, we start on 0 chemical potential. It has a quadratic band touching. And when I dope a little bit, I have a lot of states near here. I want a D-wave state because I don't have, the nodes are here, so I'm avoiding them. If it's a small Fermi surface at the center, I want S-wave because I avoid the nodes here. And in between, I get this P-wave. These are all intra-unit cell. As I approach the quantum critical point, I start seeing the P-wave. Okay? I'm going to skip. Here, we couldn't find this asymptotic regime. Okay? Sorry, he wants you to ask a question on the.
Just a quick question. Is your P wave chiral? Does it cause a full gap or does it have nodes?
So in the linearized equations, of course, we don't know. One of them has 4 components, the other has 2 components. The 4 components one, and Eduardo is going to actually mention something slightly related, but in the superconducting state. What we find is that it can be P plus IP for one spin, P minus IP for the other, but we don't know the relative phase. It could be either way. Okay? So this here is the case, and I know you also work on this problem, that if you had the P wave plus altermagnets, is actually a higher order topological state. There's something interesting, the D wave when it coexists with altermagnetism, and now if I include spin orbit coupling, I see that I get an S plus ID state. Because if I mix S and D with a relative phase of pi over 2, it has the transformation properties of magnetic octopole. Yes?
So in your phase diagram, when you are going to the region that you go to the P wave, how does this transition look like?
Oh, it would be a first order transition.
So it's always first order. And
it's just crossing, you know, you look at the eigenvalues, one is going down, the other is coming up.
Because of course you have here basically
and again,
nothing.
You have to start taking, it's not even a grain of salt, take the salt with a drop of water because I don't know how to solve the problem at the quantum critical point. So you're going to subtract all these questions, okay?
I have a very basic question. So there's R over J on both scales, right? So, but yeah. So I thought that you said in the beginning there is one coupling parameter which is your TD over T. That's not R.
Correct. So TD is fixed. My point is that as I start moving away from the quantum critical point, this R over J becomes comparable to TD over T1. So the system, you know, is in this intermediate regime between looking like an outer magnet and an antiferromagnet.
So there would be another scale that would be TD over T.
T1.
Or T1.
Which I kept fixed here.
Okay.
We did explore other regimes, and it's very much like that.
How important is inversion symmetry for getting the P wave in this phase diagram?
I have inversions. If I didn't have inversion symmetry, I wouldn't be able even to distinguish P wave and S wave. I would always have a mixture of them.
Does it kind of vanish immediately, or?
I don't think it will vanish. All that will happen is that instead of having a phase transition, some of this boundary, I mean, this actually is a tricky boundary because it's the same symmetry. It's just that because of the way that I divided the spin rotation invariance, they look different. But for example, if I have an inversion, I believe that this would be a crossover, no longer a phase transition, because there's no distinction from reduced representations of P wave and a D wave if you break inversion.
Okay, thank you.
In the ferromagnetic case without spin-orbit interaction, the P-wave transition is first order.
Yeah, yeah.
Do you know anything here?
No, because that is a consideration really when you are really getting close to the quantum critical point and you consider higher order corrections. We're just doing one loop. I want to just see what happens in the transition. It looks second order for now. I don't have any. I know, but we didn't consider that. As simple as that. I don't think that's going to happen. I think the ferro is very special because you have the conserved quantity, which you don't have here.
Yeah.
But again, this is the Voigt Kirkpatrick-Ballot story, right?
No.
Oh, this is yeah, the superconductor talk. Yeah,
Superconductors first order.
we didn't look at that. We just did the simplest, most, boring calculation. All right. Any other questions? Okay, let me tell you a little bit about the other one. I don't have a lot of time, but this is actually something that you may find entertaining. If I want to have an altermagnet, we know the conditions, right? Collinear compensated magnet, invariant under rotation time reversal. If I want to classify, and people have done it, there is this very, very nice paper by Hannah Schiff and Judith and Paul, where they classify for all space groups, all Wyckoff positions, what kind of altermagnet you get. And obviously, you want to have an even multiplicity Wyckoff position. In other words, you want to have an even number of sublattices because you're going to put spin up and spin down. In this logic, if I give you a Kagome lattice, you say, there's no way I can do that. Because, of course, if I put spin up and spin down, I'm always going to get a net spin. Can I get around that somehow? Well, there's one possibility, which is to allow the material, the spins to be non-collinear, so I can get a compensated magnet. And indeed, if you look at manganese 13, the order phase, and I think you mentioned that yesterday, right, Thomas? Maybe Libor, but we have in our review, it's right. You do get something that has the taste of this D-wave altermagnet, but it is non-collinear, so you get spin texture and not a spin polarization. Okay? We wanted, however, to think of another possibility, which is to keep things collinear, but consider the case where I do not have uniform magnetic moments. In other words, the moments do not need to be the same in every site. If I allow for that, then it's very easy to see that this state here, where I have 0 up and down, it's compensated that has a D-wave symmetry. Okay? So we were interested in looking, are there examples where I can get these generalized altermagnet with non-uniform moments that still are collinear, right? If you look in the literature, there are correlated systems that display this non-uniform magnetization. The example I chose is the one I actually was part of a long time ago. Gosh, 9 years. Iron-based superconductors. I had a small moment of depression right now. It is, you see that half.
Rafael, can you go back?
Yeah, sure.
So these are, the Kagome lattice has 3 different sublattices. Yes. So this is intra-unit cell.
Yes, correct.
So it's uniform.
That would be, exactly.
There's nothing non-uniform.
No, the magnetic moment is non-uniform, the size of the moment.
But it's inside the same unit cell.
That's fine, but in each sublattice, I have a different size of the magnetic moment. That's what I mean by non-uniform.
Okay.
It's uniform in terms of is Q equals 0.
Right.
It's non-uniform in the size of the moment. That's what I meant.
So you're breaking the point group symmetry of
I'm not. I am. Yes, I am.
You are.
Because it's a D-wave. That's why I want a D-wave altermagnet. Correct. I break C3 and time reversal together. Okay. But I want to see a realization of that. And as I mentioned, in the iron-based, the whole doped iron-based superconductors, you do get such phases. It comes from the interference between 2 collinear spin density waves. I put it here after Thomas' talk. Manganese 5, silicon 3 has also this property, right? But when you look at the Kagome lattice, there's actually a very good candidate for that, which is when you have orbital moments, when you have loop currents. Loop currents, by their own nature, do not give the same local moment or orbital moment. So they actually give you this physics. So we want to look for that. And people here like Brian and Jorg that have been working on Kagome metals, you see immediately where I'm going with that, right? So just very quickly here, the idea of the Kagome lattice is that this is the typical band dispersion of a nearest neighbor Kagome model. I have a flat band, which for my purpose, I'm not going to touch. I have a Dirac point, but I have two Van Hove singularities where you can see there is a minimum of the dispersion on one side, a maximum on the other, and the saddle points gives you a peak in the density of states. I have 5 more minutes, yes. People are asking all sorts of questions. So the key point is that if the chemical potential is close to this Van Hove singularity, I have very high density of states, so any small interaction is already going to be good enough to cause an instability. This problem has been studied a lot over the past, 15, 20 years. Because in the Van Hove singularity you have this divergence of the density of states, you can actually use weak coupling methods such as renormalization group calculation. But the key point is that when you solve this problem, here is one version where you call the patch model, but you can also do functional renormalization group. You can do Hartree-Fock. Whatever model you do, you find an instability. And it depends on the parameters what kind of instability you find. Here is where I'm interested, when you find a loop current, and you see that you always find more than one. In this case, you find a charge density wave. Okay? And this is the problem where I'm going to look for my altermagnetic realization in the Kagome lattice, when I have a loop current and a charge density wave. So these are the two phases that you get. I'm just showing you here's a charge density wave. If you have only charge density wave, it has to be a triple Q phase that quadruples the unit cell, or wave vector is half-half. And I'm showing here the bond order by coloring the different bonds, or by using different symbols for the different bonds. Okay? You could have a same version now with the loop currents. Don't worry if the loops are not closing. I can go back to that later. It's just for the symmetries here that I'm representing. But I also quadruple the unit cell. The difference now is that I also break time reversal symmetry. Now, I'm just going to show you that so that you know that I actually did something. But these two orders. Shh, don't tell anyone. Guys, how you figure it out? Oops. OK, so the key point is that on the Kagome lattice, or on any lattice that has threefold rotational symmetry, these two phases are intertwined in a sense that I'm going to define very precisely. I'm just writing down the Landau theory of these two. Each order parameter has 3 components, one for each wave vector. I have 3 of them. Right? I can have stripes these, or this direction. But the key point to see from here is why these two phases kind of come together every time is because of this. If I order the loop current, if I have both of them, I necessarily induce charge order. So if I have more than one component of the loop current, I need to induce charge order. If I have charge order, this term here minimizes the energy of inducing a loop current. Okay? So they usually come together. This kind of Landau theory has been studied a lot, especially with Brian and Morton and Turan Birol in a completely different context. And what the idea is that, OK, so if you have this idea that I first break translational symmetry with CDW order, then my loop current order will be a uniform Q equals 0 order. And therefore, it's going to be just, I should be able to classify that according to what Heido, Lieber, and Thomas classified in ferro, antiferro, altermagnet. And that's what we wanted to look. If I have this scenario where I first have CDW order, which is what we believe happens in certain materials that I'm going to mention very soon, and then I have a loop current, what is this kind of loop current in terms of these 3 phases? And I'm just going to show you the results. This is a phase diagram by minimizing that free energy. And the key parameter here is that coupling between them. Okay? And you see, I first go to the CDW phase. And depending on this parameter, I go to one of these 3 other phases. Let me just show you what they are. This is the ferromagnetic phase. So what I did here to help you visualize is that I drew on each plaquette what would be the moment. Okay? And different colors mean different sizes of the moments. So even though I have like 3 down and 1 up, they don't cancel because they're non-uniform. They don't have the same size. This one is not 3 times this. Okay? You can prove that. So this phase here, which has the 3 components of the CDW and the 3 components of the loop current, actually is a ferromagnet. Okay? Now we can go in this side here, and this is what you get. Now you have one component of the CDW and the other 2 components of the loop current, And this is actually an antiferromagnetic phase. You can see clearly here now that they cancel, right? The same color cancel, and they are related by a translation. Okay? So this is an antiferromagnetic phase. It also breaks threefold rotational symmetry, as you can clearly see here. Okay? Now this is the altermagnetic phase that we also find. This is how it looks like. Again, it's compensated, same number of colors up and down. It's collinear. But you can see here now that they are related by these two mirrors, X and Y, right? And their mirror, I'm almost done. Okay? And it's a different phase now because the relative phase of the loop current order parameters has a minus sign. So you see that you get, it also breaks threefold rotation. So you see that you get the three phases from this very simple, and then we classify all the other ones. They usually, everything below here usually is so low symmetry that doesn't happen close to the transition. Okay? But I'm going to skip this just to mention that once you include spin-orbit coupling, there's no spin-orbit coupling. This is all orbital moments. Okay? But the moment I turn on spin-orbit coupling, the sites will acquire a spin. That's just spin-orbit coupling. And you see precisely, for example, that feature that I showed you earlier. Okay? Now, to prove that this is the case, we just wrote down a tight binding model to show turn on spin-orbit coupling. And then you see the spin splitting, right? So we start with the Kagome, we include spin-orbit coupling, the gaps, the Dirac point, unflats the flat band. Now in CDW, these folds, I have now 12 bands. And I'm just going to flash this to you that if you have now each one of these orders, you see exactly what you expect, right? Ferromagnet, there is splitting everywhere. It's not uniform. And that's interesting, is because the moment is not uniform. So sometimes there are accidental nodes, okay? So it's an S-wave ferromagnet with accidental nodes. It's perfectly allowed. Antiferromagnet, there's no splitting. And the D-wave altermagnet, there are regions where it's split, regions where it doesn't split. This is the Brillouin zone. The small one is the one in the CDW phase, in case you want to see. To give it more visual, this is how the spin splitting looks like. It's very similar to what was shown yesterday. In Thomas' talk, you get a D-wave that breaks threefold rotational symmetry. Okay? And just to mention that we were motivated by these materials. They are Kagome superconductors, cesium, potassium, rubidium, vanadium-3, antimony 5. They are superconductor, but they also have CDW phase. This CDW phase has been reported by different experiments to break time reversal symmetry. It's an issue that people are still discussing, but we believe that this is actually the altermagnetic phase, or it could be one, because it would explain why you don't see the presence of an anomalous Hall effect or Kerr effect. Okay? This kind of D-wave does not allow for that, but it allows for the effect of piezomagnetism that was observed by Vidya Madhavan in STM. Okay? So what we're proposing, and these materials actually people can do ARPAs very nicely. Ricardo Comín has papers on that. So do spin resolve ARPAs to see if you can find these splittings. And with that, I'm going to leave with my summary and take more of your questions. Thank you.
Just a quick question. In your loop current state, without spin orbit coupling, you had no spin splittings, right?
Correct.
And so the spin splittings you show came from spin orbit?
Correct.
And was that a relatively large spin orbit coupling you used there?
We put a little bit larger so you can see.
Okay.
This is the spin orbit coupling of the just the Kane-Melle type. It's similar to one that Marcel had in his paper, but we considered it. I don't have it here. Sorry. It's a nearest neighbor one. It's just a Kane-Melle on that particular kind. So yeah. So sorry. Yeah. So that's what it was interesting. That if you have an orbital altermagnet, you need a spin orbit coupling to see the spin splitting, right?
Naive question. When I'm dealing with normal and altermagnets, I know how to control it externally. So I apply magnetic field or spin current. What can I do when I have this orbital nice picture? How can I control it effectively?
So the same way. I mean, the magnetic field will couple to the orbital moments. And in fact, there's going to be, in this particular material, they saw this by applying a magnetic field and seeing these Bragg peaks changing their intensity. So it's the same. It doesn't really change. It's strain and magnetic field. Now, the magnetic field is not going to come as a Zeeman effect. It's going to come as an orbital effect. So it's a little bit different. But it's still, from a symmetry point of view, they're the same thing.
I have a question, well, a comment. Can you flash the pattern of the orbital, of the loop order that you have?
This one?
Yes. Okay, so you look always, the way I think of it is that your moments are actually, you could think of them as fluxes going through these different plaquettes.
Correct.
Okay?
And that's how we try to represent it.
Right, okay, so instead of looking for a case where they precisely compensate so the total is 0, you can imagine the total to be 2 pi.
Correct.
Okay?
Absolutely.
Now, in that case, this has been studied, at least at the level of the one particle theory, you end up with propagating states which are actually Chern bands. Then the flat band is trivial, okay, but the non-flat bands, the usual bands, are actually have a Chern number 1 and -1 in that case. And
Like here, right?
And
Like here, right?
yes. And when you quote dope that system, I studied that with a student, and Luis Santos was a postdoc, and Raman Sohar was a student. So in that case, you end up getting what people nowadays call fractional Chern insulators.
Yeah.
Okay, and you get a whole bunch of them. So I was wondering if that may not be relevant to this story.
It's an interesting point. We didn't think about it. It's actually very interesting.
It's an analog of the Haldane model.
Yeah, and to some extent, because the CDW already triples the unit cell, my loop current really doesn't do more than just adding a flux. So I don't see why not. The problem is when you fold it, though, like we're doing, it's not guaranteed that you're going to get, there's some bands that are isolated, some still cross, but I don't see why you wouldn't be able to get that.
This way you have to do flexible.
Right. So I don't see why not. We didn't look at that. But it's an interesting point. If you give me your email, I can email, we can talk.
Do you know Eduardo?
I met him before. Okay. Every time I do this, Elena jumps, so I'm going to be careful, sorry.
So I have a related but maybe simpler question. So that thing there with the Kane Malay on Kagome, that's a Z2 topological insulator. So is there any of that topology, does it remain in once you break time reversal and fold your...
So here it didn't break time reversal. Here it's simply just folding from a bond order. So it's just increasing the size of the unit cell. So I don't believe then that you would get rid of the Z2 topology because all I'm doing is enhancing the unit cell. I believe so, but we haven't looked at that.
The charge density wave only.
Yes. Yeah. Now, once you have the loop current, the fluxes, then I think it's more in the direction that they're saying. But it's a good point. We didn't look, and it should be pretty straightforward to look at that.
The anomalous Hall effect. So your loop, you said it was excluded, and I saw that for the orbital moments, you have these two mirrors, right?
Correct.
Which exclude the anomalous Hall
Exactly.
effect. Now, my question is about the spin. When you add spin-orbit coupling, the spins are also pointing out of plane, but that depends on the type of spin-orbit coupling, right?
Yeah.
Absolutely.
So if you had another type of spin-orbit coupling, you would have them in plane, you would have an anomalous Hall
You
effect.
could.
You could break
Absolutely.
one of the
So,
mirrors.
yes, I agree. Well, it depends on which in plane, right, as you mentioned, right? But we're really considering like a 2D system, then I don't think you can get any other kind of spin-orbit coupling than, unless you put more orbitals. This is a S-wave orbital, so that's
it's a 2D.
It's a 2D. Then that's, as I mentioned, the Kane Malay. So it's not a S.L, but it's the one where you go around, right? Now, you're right. If I have different orbitals and in real material not going to be either pure 2D or S-wave, then I could have the moments pointing in the plane, and then it will depend. Actually, even when it's out of the plane, I can also get ferromagnets. Because, you see, this is one domain. I have 6 others, and it's exactly the same story. I can have 6 domains in the main axis or the perpendicular direction to the main axis. In one case, I break an extra mirror. You can see here, right? If I align with the mirrors, then it's forbidden. But if I go to the 30 degrees, I break the mirror, then I do get a ferromagnetic moment. So you don't even need to include an in-plane moment. It's really thinking of how the 2 sets of 6-fold. It's a 6-state clock model. It all depends on which set of minima you are.
So for the state without spin-orbit coupling, so you constructed is to have the D wave or the altermagnetic symmetries. Yeah.
Yes, that's what we.
Is there anything that is non-trivial in terms of altermagnetic symmetries? For example, if I look at sublattice polarization of the band structure, or is there like an orbital analog?
Sure. There has to be an orbital analog. We looked a little bit, and it was not very obvious what it was, to be honest. But I agree with you that there has to be, like an orbital splitting, right?
Exactly.
We just couldn't define it properly to find it, and maybe it's just our inability to find the right quantity to look at. But I agree with you.
Okay, because in principle, the only thing that you have left is the sublattice degree of freedom, which you could label.
Correct.
To bands.
Now, and that's the problem, is that my Hamiltonian is not diagonal. I mean, sublattice is not a good quantum number, right?
Yeah.
So maybe that's the reason why you can't really label the bands in that way to see any feature. But, could be.
Okay, thanks.
I find it very interesting how you, let's say, twist all what we know from this charge density wave. You have a very nice way of twisting it towards maybe talking about an altermagnetic or the parameter. Now, my question is, let's complicate things a little bit, because so far you have been thinking always in terms of Ginzburg-Landau or one particle. So what about now starting to introduce interactions here in your problem? How would you start? And because we know from the moment that you're presenting materials, we need to think about that. So
absolutely. So I'll tell you what we know and what we don't.
Cada uno con su tema.
These are the known knowns and the unknown unknowns.
Exactly.
So let me put it this way. Let me take a step back and say, what do we know? I mean, these are not strongly correlated. I don't know. Thank you.
You can use that.
So, these are not strongly correlated systems,
no,
right?
It's vanadium. It's
exactly.
Okay.
So
I can live with
one
that.
thing we did with Turan was, I know the Ginzburg-Landau. There is actually an identical Ginzburg-Landau. If instead of this being loop current is the CDW with the wave vector out of the plane, the L point. Yeah. And one thing we did, because, as you said, everything from DFT, we actually were able to fit all these parameters with DFT and get a phase diagram of the Landau theory. Of course, then you have to assume some temperature dependence, but that gives you actually what would be equivalent of what I call the antiferromagnetic phase. The problem to include loop currents, and that's what we talk a lot with David Vanderbilt also, is we don't have a functional in DFT that gives you a loop current. So we are stuck there on that point. So if you want to talk about specific materials, that's where the funnel is right now, is how to properly define a state that has a loop current. There are some, there are some attempts, but nothing, there's still a hole there, right? Now, if you want to talk a little bit more about models, right, in terms of interactions, to some extent, it all depends on which kind. So we have, here we use the patch model, but Ronnie and others use FRG, and Hai-Young Key and Young Bakimi use different kinds of interactions. It really depends on which interaction is the largest one. You can get loop current, you can get CDW, you can get spin density wave. So without knowing which one is large for that material, I can't say anything, right? But again, within recoupling, which of these phases is chosen does not depend a lot on the interaction. Interaction just gives me the instability channels. These combinations all come from higher order terms that in principle I should be able to get from DFT, for example, if it's a weakly correlated system.
One last short question.
Can I go back to the first part of your talking?
Oh, my favorite one. Fine.
I have a question about that. So you pointed out that the antiferromagnetic fluctuations give you S wave. The altermagnetic gives you something richer.
Singlet. I said singlet, not necessarily S wave. It could be.
Sorry, singlet.
Right.
Now my question is the altermagnetic coupling a relevant perturbation in the RG? So it's
a Yukawa kind of coupling. So yeah, absolutely.
Okay.
To the Fermi liquid fixed point. Yeah. Okay. That's what I thought. That's what I thought was the question, right?
Perfect. Good. With that, let's thank Rafael again.
Thank you.